Um, so there's a problem here. It says find absolute maximum and absolute minimum values of a certain function
Okay.
in a certain like area.
All right. What's the
So
function?
x cubed plus 6x squared plus 1
Okay. What's the domain?
from -5 to 3.
Okay. So we want the absolute maximum and the absolute minimum
Yes.
in that interval. Okay, what's the concept that we're going to use here? How are we going to do it?
First use the derivative.
Okay, the absolute maximum and minimum are going to come at one of four places. It's where the first derivative is equal to 0, or maybe the first derivative is undefined, or the endpoints. So those are the things we have to check. All right, the endpoints is pretty critical. What's the first derivative?
3x squared plus 12x.
Where is that equal to 0 or undefined? What do we have to do here?
Well, set that equal to 0,
Okay.
and then I factored out an x to have x times 3x plus 12.
Let's factor out a 3x. Always factor out your greatest common factor. Okay. Which means that 3x equals 0, or x equals 0, or x plus 4 equals 0, or x equal minus 4. So there's the 2 points where the first derivative is equal to 0. There's no points where the first derivative is undefined. So we only have to check 4 numbers. We have to check x equals 0, x equal minus 4, x equal minus 5, and x equal 3. The reason is that if you have a function that looks like this, well, if my interval goes from there to there, A to B, that doesn't represent an absolute maximum at all, nor does that represent an absolute minimum. This is the minimum right here, and that's the maximum. So you have to check your endpoints also. And the way to check all of these is to plug it in. Do I plug it into the derivative, or do I plug it into the first equation?
First equation?
Okay. What is f of 0 equal to?
1.
What is f of negative 4 equal to?
Hold on.
Plus what? In other words, we have negative 64
Would it be
plus 6 times 16
96?
plus 1.
161?
No. Negative 64 plus 96 plus 1 is 33.
Yeah, that's right.
Okay. I think, unless I did my math wrong.
I did it right.
Okay. And what is f of, we have to check the endpoints. What is f of minus 5? Okay, what do we got? We got minus 125 plus 6 times 25 plus 1. That's equal to 26. And finally, f of 3. Is 27 plus 6 times 9 plus 1. That's 55 and 27, 82. The original question was, what's the minimum and what's the maximum on that interval?
Yeah.
What's the minimum?
0.
What's the maximum?
3.
Correct. You notice the minimum does occur at the first derivative equal to 0, but the maximum occurs at an endpoint. Okay, what else? I'm guessing that if you got that problem wrong, you probably only used the two that were the first derivative. In other words, you probably put the minimum of 1 and the maximum at 33.
Yeah, I didn't use the open.
You got to use the endpoints.
Yeah. Can't do that. I just had problems with graphing a function.
Okay.
So it like gave you a bunch of details about it, and then using those details you graphed it.
Yeah, if I'm not mistaken, we had one like this, and it looked kind of like that. Remember that one?
Yeah.
Okay. It wasn't a parabola. It was a shape that had a oblique asymptote. In other words, the oblique asymptote was like that, and the function was more like this. Remember oblique asymptotes? The function approaches that asymptote as it goes to infinity. They wanted you to find the minimum on this. And at the time, a lot of times I'll get confused as when we're in a calculator problem and when we're not, or when we're in a non-calculator problem. This required a calculator. Not only, we were able to graph it, but in terms of figuring out what that point is right there, you would need to graph it in a calculator or on your computer and figure out the minimum. Because they didn't give us the function, if you'll remember right. They gave us all kinds of facts about the function. And they didn't tell us what the function was. If they gave us the function, then this minimum is relatively easy to calculate. You take the derivative, set it equal to 0. But without the function, this was very difficult to figure out, if I remember right. I might be remembering some details incorrect about that, but what do you got this time?
So the domain of the function is from -1 to infinity.
Okay.
And do you want me to just list, because there's 14 different.
Oh my goodness.
Yeah. So f of 0 equals 2. And then f of 2 equals 2. F of 3 equals 3.
This is probably one where you We'd be better off taking a picture and sending it, but that's okay. We've started verbalizing it. Let's go.
Okay. F of 4 equals 2. And the first derivative is less than 0. And then the domain of x is between -1 and 1.
I thought the domain was between -1 and infinity.
It says, so it gives you the derivative is here. I'd rather, can I send you a picture real quick?
Sure.
There we go.
Did you send it yet?
Yeah.
Send it to David Cowan 1949 at Gmail.
Yep. It says it's still sending.
Yeah. Yeah, it with attachments it takes a little bit of time. So they're going to give us 14 facts about this function and they want us to draw it, huh?
Yeah.
Without a calculator.
Yeah.
Okay. Is the domain of the first derivative perhaps -1 to 1? No, that wouldn't make sense. Okay, I got it.
I think the picture's sent.
Yeah, no, I got it. Let's pull it up here. Sketch a possible graph. Yeah, that was the domain of the first derivative.
Okay.
In other words, it's, well, it's not really the domain. It's saying the first derivative is less than 0 between -1 and 1. Okay? First derivative is greater than 0 between 1 and 3, and the first derivative is less than 0 between 3 and 4.
Oh, okay.
Okay, first derivative is greater than 0 when x is greater than 4. First derivative evaluated at 3 is equal to 0, the limit, all of these other things. All right, let's see if we can come up with a sketch of this thing. All right, let's see. If the first derivative, let me label some points here. I'm just going to take it one piece of information at a time. Okay, let's start with that one. If it's less than 0 between those 2 points, what is the original function doing?
The decreasing?
So we'll put something like that. It's definitely decreasing. Okay. From 1 to 3, it's got to be increasing. So we'll do that. From 3 to 4, got to be decreasing. So we'll do that. And that covers those 3 things. Now, let's look at these. F of 0 equals 2. Well, the way I drew it, that's correct. F of 2 equals 2. Well, the way I drew it happens to be correct, pretty close to correct also. And I was just randomly drawing those lines. F of 3 equals 3 happens to be fairly correct also. F of 4 equals 2. Okay. So far, our curve looks pretty good. So far, our curve agrees with all of those and all of those. So let's look at the rest of them. Greater than 4, it's increasing. So we'll go like that. F prime of 3 equals 0. What does that mean for my chart?
It's either that's a relative extrema.
Well, it's not necessarily a relative extrema, but the tangent line is horizontal.
Okay.
Right? In other words, there's a couple of ways you can get tangent lines horizontal. If I take the curve y equal x cubed, looks like this. Well, the tangent line at 0 is horizontal, but it's not a relative extrema. It does not pass the first derivative test. This has slopes going plus, 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 and coming out plus, plus, plus. The slopes have to change going in or coming out. That's the first derivative test. Okay? If I had this going on, well now, the first derivative test, it goes plus, 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 but it comes out of it minus, minus, minus. So before and after, if you go from plus to minus, you're looking at a local maximum. If you go from minus to plus, you're looking at a local minimum. But if you go from plus to plus, it's neither, or if you go from minus to minus, it's neither. So the first derivative has to change signs on either side of the 0 point. So, going back to our graph, is all I know is that the first derivative at 3 equals 0. Well, let me draw that a little different. Let's see, I know it's increasing between 1 and 3. And it goes through that point there. So how about there? Now the first derivative at 3 is horizontal. And I can still say it's increasing. Let me redraw that slightly. Okay, I know it has to go through there. Has to be increasing up until 3, and then it goes horizontal. And we don't know whether it comes down next or keeps going up. We know it kind of comes down, so the most likely pattern is going to be this. Okay? Now we have satisfied our first 8 conditions and that one. Now let's look at this one. The limit of, as we go to 1, goes to negative infinity. Well, what about if I draw this curve with a vertical asymptote at 1, and the curve is going to go Always increasing to there. Now we've satisfied that. The limit as we approach 1 is negative infinity. Can you see that in the graph?
Yeah.
Okay. Second derivative at 0 equals 0. This piece of information right here. Well, that means there's an inflection point at x equals 0. It's where the concavity changes. Okay? Well, here's my line that goes through x equals 0. I've drawn it as a fairly straight line, but let's draw it with a changing concavity. In other words, I'm still going to have it decreasing, but now I'm going to have it do that. Notice why that's an inflection point. It's halfway between concave down and concave up. And in fact, let me make that the opposite. Let me draw it concave down, concave up, the first part of it. The second part, I'm going to draw concave down, like that. Yeah, okay. So now I still haven't violated any of the conditions that I've drawn, and I've incorporated the inflection point into my curve. Okay, let's look at this one. The second derivative is less than 0 whenever x is greater than 1. Well, the second derivative being less than 0 means what?
It's concave down.
Correct. Okay. Whenever x is greater than 1. So I've got this part of it right here is concave up, so I need to redraw that. Okay, so let's redraw this whole thing. I know it's going to be asymptotic with that line. I know it's going to go through 2. I know it's always going to be increasing. It's going to be flat at 3, and it's going to be concave down at 4. And then this part has to be concave down also, while still being increasing. With me?
Yep.
So all I'm doing is starting with the first point of information, attempting some sort of drawing, and then gradually changing my drawing as I find each additional piece of information. Okay, the limit of f of x equals 4 at x going to infinity. Well, that means there's a horizontal asymptote at 4, and this part is going to approach that horizontal asymptote, always still increasing and always being concave down. In other words, that piece of information tells me there's a horizontal asymptote. Because what horizontal asymptotes are is what x goes to as it goes to infinity. In other words, if I go to infinity to the right, I'm always approaching the line y equal 4. And finally, the limit of f of x also equals 4 as we approach negative 1 from the right side. So as we approach negative 1 from the right side, oops, that's from the left side. If I approach it from the right side, this has to change into something like that. Yeah. Let's see. Let's change the concavity. In other words, I didn't know if that was concave up and that was concave down or the reverse. Let's reverse it, and I think it looks a little better. Make that concave down. Make that concave up. So we still satisfy all the conditions, but now as I approach -1 from the right side, I know that much right there. And I think that's all I know. Let's see. The domain was -1 to infinity, so there's nothing left of -1. Let's see what kind of graph you came up with and see how it looks to mine. Not bad, actually. Looks like you did the proper stuff. In other words, our graphs don't look that different. In fact, they look pretty darn similar. So it looks like you had the correct stuff. Notice why she circled that.
I didn't use the horizontal asymptote.
No, the second derivative was negative, so it had to be concave down. In other words, the second derivative was less than 0 when x is greater than 1. So it has to be concave down everywhere to the right of 1.
Mm-hmm.
And I can certainly connect these 2 points here so that that's true. No, it's concave up there. So I can't connect them. I have that much. We know that f of 4 is equal to 2. So we know that there is a point right there. But it could be a piecewise function, could it not? In other words, could it not be something like that? So that we don't have any concave up. In other words, we've got to be concave down everywhere to the right of 1. Now, as to whether we can draw this whole thing or not, I don't know. Let's see. We're going from -1 to infinity. Is there an asymptote at -1? Not necessarily. Just because the domain only goes from -1 to infinity, lots of things could cause that. In other words, if I put this, the domain goes from, hold on, excuse me. Yeah, if that were the function, the domain would go from -1 to infinity, correct? So there doesn't have to be an asymptote there. It could just be a dot. Kind of like when you plot the square root function, starts as a dot and goes up like that. And the domain of the square root function is 0 to infinity. So it could be that. Now, she circled in green the parts that your graph doesn't agree with. Is that correct?
Yeah.
Okay, let's look at this one here. We need concave. If the first derivative is negative between these 2 points, then it has to be decreasing. Yours is, she circled that because it looks like a vertical line. You cannot have a vertical line and have a function. We know we have a function. Could be a piecewise function, but it can't violate the vertical line rule. Notice that what I've drawn over here does not violate. I can pass a vertical line left to right and not come across 2 points on the y-axis. Okay, so that's partly why she circled that and said it was not a function, and why she circled that. Now let's look at this. Your domain is supposed to go from -1, but with a parentheses. Which means it can't be a dot like that. It means there is no f of -1. Which leads me to believe that maybe there is a asymptote there. Although I'm trying to figure out how that would work, because we know that as we approach -1 from the right, we're approaching 4. So I don't quite understand. Let's make it a circle, an open circle. That's one way to solve that problem. I'm going to make it an open circle like that. Now, our domain of this function is parentheses -1 to infinity. Okay, so I don't violate that. Let's see what else she didn't like. She didn't like the fact that you had the limit of f of x equals -infinity as x approaches 1.
Oh, I didn't put an asymptote.
Right. Not only is it an asymptote, but it also tells us that as we approach 1 from the right and the left, it's -infinity. But this thing has to be concave up the whole way. Let me go back and redraw this part of the line the way I originally had it, which is concave up to the inflection point. No, I'm sorry, which was concave down to the inflection, no, concave up to the inflection point, concave down after that, and since this says the limit is -infinity as x approaches 1, well, the limit exists and it has to be the same from the right or the left. So drawing the curve like I've now drawn it, the limit at 1 is -infinity from both sides. And I still have it always decreasing, and I still have an inflection point there. So I think I've taken care of that problem. This merely means the inflection point at 0. There's 0 on the x-axis. There has to be an inflection point right there.
I just drew that vertical line. So.
Right, okay. And we have to be concave down to the right of 1. That looks correct. Let me put a circle there so that, we don't have any concave up at all. And And the limit of f of x equals 4 as x goes to infinity. That's taken care of by that horizontal asymptote at 4. And finally, this one here. That's the one I'm not quite sure what to do about. The limit of f of x equals 4 as we approach -1 from the plus side. Well, I guess this takes care of it. If I move that 0 up to being right there, then it never actually reaches 4, it just approaches it. So I would say that my curve satisfies every condition we see. Do you by chance have the answer? Do you have the...
No.
Yeah, this is going to be a toughie because they don't give us the function, so I can't even plot it on Wolfram alpha. But there's a reason why they don't give us the function, is because they want us to plot it based on all of that other stuff. Now, this doesn't have to be the function that they're referring to. It only has to meet all 14 conditions. There's 7 there, there's 7 there. And from my perspective, there's actually 15 conditions, because we know the domain of the function goes from -1 to infinity with a parentheses at the -1. And so I think if you go through all 15 conditions, this graph does not violate any of them and supports all of them. And that's kind of the way you need to do these. Okay? You weren't that far off. Your graph was close. Did you get any credit on this at all?
Yeah, 11 out of 16 points for it.
Not bad. You had, notice your graph and my graph look pretty similar except for that vertical asymptote at 1. And the fact that you drew that as a vertical line, but you could have easily drawn it the way I drew it. Put a vertical asymptote there, and now we're almost exactly the same. That's wrong because that would be concave up, right?
Yeah.
And the condition is that it's concave down everywhere to the right of 1. So this can't be right. This is the only picture I could figure out that makes it concave down everywhere to the right of 1. Well, we can't get this part here if we connect. In other words, if it's not piecewise, then we're going to have a concave up somewhere. There's no way to avoid a concave up. The only way I could figure out how to make it concave down everywhere is to make that a piecewise function right there. And she circled that because that needs to be concave down like that. She wouldn't have circled it if you'd have just made it slightly concave down. All right. I think we've covered that problem to every aspect that I know. It may not be right there. I'm not real sure about that, although no, that actually looks correct. It is approaching 4 as we approach -1 from the right side. And yet there is no value of f of -1 because the domain doesn't allow for it. So it has to be an open circle as opposed to a closed circle. If it was a closed circle, then the domain would go from bracket -1 to infinity.
Okay.
Okay?
Can you leave that graph up real quick so I can take a picture?
Yeah.
So I can get to it.
At this point, was on the graph. You got it? You good to go?
Just give me a second real quick here. It's not.
By good to go, I meant good to go to the next problem.
Yeah. Yeah, we're good.
Okay, cool. What else? That was a hard one to do online. I have to. Well, not really. Once you sent me a picture, you actually could have verbalized all 14 of those conditions. It would have just been time consuming.
Yeah.
What else?
I could do. So that was all I basically missed on that test.
That's good to hear.
So we have another.
Must have had a pretty good. What'd you get on the test? Is that like a B or an A or a C or?
It was a C.
That was a C, and that's all you missed? Was those two?
Yeah, there weren't very many problems. It was like a quiz.
Okay.
Because we have our big test on it coming up next week.
Yeah. All right. What subject material have you been covering, and what are you about to cover?
So we're still.
You're still plotting. You're still graphing based on first derivative function and second derivative information.
Yeah, and then also using mean value theorem.
Okay.
And then optimization as well.
If you have an optimization problem, those can be kind of challenging. We should do one. If you haven't been quizzed on optimization problems yet?
Not yet.
Have I given you my cardboard box, the classic optimization problem? Maybe not. I don't remember doing it.
I think we might have done that.
Where you cut out a corner of each one to make an open top box. Let's say we have a 10 by 8 piece of cardboard. We're going to cut out a square section of each corner, and then we're going to fold it up along those dotted lines, and we're going to have an open top box. Have you done this problem at all?
I think so.
Okay. Is there another optimization problem you'd like to do? I mean, there's a bunch. There's also the fence problem where you're trying to maximize the area of a corral, and you have a certain amount of wood. Have we done that one, or have you done that one?
Yeah, I have an example of that one, if you want to do that one.
Yeah, let's do that one.
Okay. Do you want me to just read it to you?
Sure.
Okay, so a rancher plans to fence in 3 sides of rectangular pasture.
Okay. So
with the 4th side being against a rock cliff.
Okay, or a river.
Yeah.
Okay, so here's our picture. Okay.
He needs to enclose 320,000 square meters of pasture. What dimensions would require the least amount of fence material?
Okay. It's a little different. When you have an optimization problem, you have to come up with the function. Well, what is the amount of fence material he has if I put this on the coordinate system? Like that. Okay. In other words, what's the formula for the perimeter of that 3-sided rectangle?
X plus 2y.
And what's another formula that relates to this drawing?
X times y equals 320,000.
Which of those two equations are we trying to maximize or minimize?
The perimeter.
Correct. Okay. So, in order to find a relative extrema on the perimeter function, we need it to be in one variable only. Right now it's in two. It's in x and y. But we have a second equation. So let's solve the second equation for y, which is 320,000 divided by x. Substitute that into the perimeter equation as a function of x. Now becomes x plus 640,000 over x. Okay? You see that? How we now have a perimeter function that's a function only of x. You with me, or do you need me to?
Did you just, to get rid of 2x, multiply it by?
Actually, what I replaced was the 2y.
Oh, yeah.
All I did was I solved this equation for y, and then substituted. So 2 times that is this.
Okay, yeah.
Okay? The key thing is that we have our function that we're trying to minimize or maximize, and it's a function of one variable only. So our goal is to take the first derivative, set it equal to 0, and find out whether, first of all, that's a maximum or a minimum. And then that will be our answer when we find out that it's a minimum. And we'll find that out by taking the second derivative. So what's the first derivative?
1 plus, negative 640,000. So yeah, minus. X to the negative 2 or x over 2.
Like that. Okay? Let's see, because that was x to the negative 1, so it becomes negative 640,000 x to the negative 2. Okay. Now, we're going to set that equal to 0.
Okay.
And the question is how we set that equal to 0. Well, if I want to solve this equation, I can multiply everything by x squared. With me?
Mm-hmm.
Which means x squared equals 640,000, which means x equals 800. Now, is that a maximum or a minimum? Let's take the second derivative and plug in 800 into the second derivative and see whether it's positive or negative. In other words, we're going to apply the second derivative test to determine whether it's concave up or concave down. If it's concave down, then it's a maximum. If it's concave up, it's a minimum. Well, what is the second derivative? I think. No, it's
640,000 just be multiplied by 2.
yeah, it's twice that. So it's a 1 million. That's it, right there. When I plug in x equal 800, is that positive or negative? In other words, P of 800 is greater than 0, correct?
Mm-hmm.
I mean, there's no negative sign, so it's positive, which means it's concave up, which means it is a minimum. So that's our answer. Now, I had another way of testing that. I could have gone into the original function and plugged in 799 and then plugged in 801 to check to the left and to the right of the point 800. And as long as my derivatives go negative, 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 0, positive, 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 then it's a minimum. So I don't have to have the second derivative test, but it's certainly the easiest thing. The only time you really have to use the first derivative test is if the second derivative test comes out to be exactly 0. And if you cube 800, you don't get 1,280,000. You get at least 6 zeros. In other words, you get 8 cubed times 10 to the 6th. So this is not equal to 0. It's greater than 0. If it were equal to 0, if P double prime of 800 were equal to 0, then I would have to go back to the first derivative test and determine whether it indeed goes minus, minus, minus to plus, plus, plus.
Okay.
Okay.
Yep.
That's actually a little bit of, that's not quite the classic. The classic problem with the corral is they give you a certain amount of feet of fencing material to work with. And the question is how do I build my corral so that I get the maximum amount of area? And that's usually the real life situation. Usually a rancher will have a certain amount of wood that he has, right?
Mm-hmm.
And you got a bunch of wood laying in the barn, you want to build a corral. How do you design the corral such that it's the maximum area? Well, you're always wanting the maximum area for your cattle. Well, this one gives the area, and they want you to find out the minimum amount of wood to make that area. Notice that I could draw it this way so that I have the same area, but it would be a lot more wood. So I'm never going to want to make an area of 640,000 or 320,000, whatever it was, with this kind of a rectangle. I'm always better off making it that way. And the way we made it, we figured out x was 800. So that side's 800. And we know that x times y is 320,000. So y must be 400. 400 times 800 would be 320,000. So that's the dimensions of our corral. And oddly enough, regardless of how you state the problem, the horizontal dimension ends up being twice the vertical dimension.
Every time?
Every time. In other words, if I told you you had 1,600 feet of wood, right? 800 plus 400 plus 400. And I said, make me a corral out of 1,600 feet of wood and maximize its area. Well, I would make the corral where the horizontal measurement was twice the vertical. This is only for three-sided rectangles. If it's a four-sided rectangle, it's always a square, is what maximizes it. But if it's a three-sided rectangle, you maximize the area by making the length twice the height. But the problem would have been the area equals x times y, the perimeter equals x plus 2y, and we were given the perimeter number. So we know the perimeter is equal to 1600. Find out what the maximum area is. Well, we do the problem almost exactly the same. We use the second equation to solve for x or y, and then substitute it into the area equation, and then we take the first derivative of the area equation and set that equal to 0 and see what that maximum area is going to be. And it would come out to be 320,000.
All right.
Okay. As we only have 3 minutes, so we won't start a whole new problem. But the box problem is a really good one to illustrate this concept. For one thing, this is the way they make open top boxes. Is they cut a corner out of a flat piece of cardboard and then they fold up the edges. So there's no top to the box, but there's a volume. Well, the cardboard piece I have is 10 by 8. Since we're trying to optimize the volume of the box, the volume is base times width times height. Base, that's x. So the base is what? 10 minus 2x.
2x. Yeah.
The width is what?
8 minus 2x.
And the height is what?
Oh, just x. Oh, okay.
Yeah, you're going to fold it up on these dotted lines. So the base of our box is going to be the dotted line. And this side would be folded up, this side would be folded up, that side folded up, this side folded up. You end up with an open-topped box. Okay? This is the classic problem because it immediately is all a function of x. There's no other variable to take into account. Well, now you merely multiply those three things together, take the first derivative, set it equal to 0, and you find out what x is to make the maximum volume. And you'd be surprised, it's not an even number. It's, in other words, this is not a problem you could figure out without calculus. I know of no non-calculus way to answer this problem. And you get an x that's like an odd number, like a 1.4 or something. It kind of depends on the width and the base of the cardboard box. But you can't even solve this with precalculus. Because notice that when I multiply these three things together, I have a cubic. I have at least an x cubed term. If the volume was a quadratic, well, I know how to find the vertex of a quadratic, so I don't need calculus to do that. But when you give me a cubic function, I do need calculus to figure out where the local extrema are.
Okay.
Okay? All right. It's a good place to stop. Looks like you're doing fine. She gave you 11 out of 16 on that. That's not bad. That was a hard question.
Yeah.
It really does illustrate your knowledge of function, first derivative, and second derivative. In other words, in order to be able to answer that problem, really needed to know the implications of all 15 of these things. All right. I will talk to you next Friday at the same time.
All right. Thank you.
All right, Jackson. Bye-bye.